Hey there, Y10s. In this video here, we're looking at exercise 8G, which is called independent events. At the end of the day, independent events is a very easy formula to use, but I think it's a bit of a concept to understand only if you didn't understand conditional probability and tree diagrams. Okay, but assuming that you've done conditional probability and tree diagrams, if you haven't done that, that's okay. I can try to describe it as we go here. So what's independent events? Independent events are when two events, like event A and event B, they satisfy this one formula, okay? And it's this concept. Probability of A given probability of B is equal to the probability of A. Sounds simple, but let's rearrange that formula. And if you remember from conditional probability, that's 8E, I think it was. Let me just check. D. So if you've done D, then this will help you understand. So probability of A given B, remember the rule was probability of A intersection B divided by probability of B, right? And remember how I said you can multiply both sides by probability of B? Well, then that gives you probability of B times probability of A given B will then equal to probability of A intersection B. So that's from conditional probability. Yeah, but here, independent events is saying, well, what if this probability of A given B, so what if that is actually just probability of A, right? Then the formula now becomes this. The formula becomes this. Probability of A intersection B is actually equal to probability of B times, make it easier for you to remember, probability of A times probability of B. That's essentially what the rule is. Okay, so I wrote here, actually, I already gave myself space to do this, but that would have been probability of A intersection B divided by probability of B. And then if you rearrange it, probability of A given B multiplied to probability of B will equal to probability of A intersection B. Okay, now, here's the logic. I'm going to try to re-illustrate conditional probability again. So I'm going to use a tree diagram to illustrate it. Okay. Let's say that you are going to, let's say it's going to rain on Monday. So you got Monday and then versus Tuesday, right? So you either have on Monday, it either rains or it doesn't rain. Okay, fair, cool. Let's say then the next day, Tuesday, it could either rain or it doesn't rain. This means, but then on Monday, it could have not rained and then the next day could rain or it might not rain. So this is our tree diagram, right? These are your scenarios. Now, what you have to realize here, assuming in conditional probability, when you say conditional, right, conditional probability, what that actually means is that the event of one, so the probability of Tuesday raining has some linkage to whether Monday rains or not. And in some ways, there's probably a linkage. If it rained yesterday, it may mean that tomorrow is going to be less likely to rain. I don't know. There's probably a linkage. Yeah. So probability, conditional probability is the idea that, well, the chances of Tuesday raining, given that Monday had already rained, what's that chance? That's essentially what you're asking there. I'm going to change the letters actually just to make it easier. So M and not M. Okay, so meaning rains on Monday or doesn't rain on Monday, and then this could be Tuesday. Yeah? Tuesday rains, Tuesday doesn't rain, Tuesday rains, Tuesday doesn't rain. Yeah? All right. Now, conditional probability, if you were to calculate this, right, you would say, what's the chances of it? If I said, what's the probability of Monday raining and Tuesday raining? What you would have done is, let's say I gave it, let's imagine I said it was 80% chance Monday is going to rain. That means there's 20% chance it won't rain on a Monday. And then let's just say, I don't know, 60% chance it's going to rain if it rains on Monday. And then there's 40% chance it won't. But if it doesn't rain on a Monday, well, then there's a very low chance it will rain on Tuesday, the next day, and then maybe 0.9. 90% chance it won't rain on Tuesday. Okay, let's do that. I'm just making up the probabilities here. If I asked you to find the probability of Monday raining and then Tuesday raining, what you would have done is you would have done this. You would have said probability of Monday raining is 80% chance. Okay, out of that 80% chance, now the chance of Tuesday raining is 60%, but 60% of the 80, right? Because Monday was 80% chance. And out of that 80, you're going to have another 60% chance of that 80 for that to occur, for both the days to rain. So then we would have done 0.8 times 0.6. But what you should realize here is what you're actually doing there is you're doing probability of Monday raining times, and when you have to realize this 0.6, this Tuesday raining is not probability of T, because this is probability of T as well. It's actually probability of T given that Monday did rain. Can you see that? This 0.6 is actually saying probability of Tuesday given that Monday had rained. That's what it actually means. And so when you multiply the two, you get your probability. Now let's get our calculator out, and 0.8 times 0.6, which is 0.48. Okay. You got 48% chance that it's going to rain on a Monday and a Tuesday, right? This is where independent events is different. So independent's like the opposite of conditional probability. So if you understood what I just said there and how you would have calculated, you have to realize this step is the key part. This step. That 0.6, in your understanding, it's Tuesday, is somehow relevant to what had happened on Monday. There's a linkage. Then that would be conditional because it's clearly there's a linkage between it. But in independent events, what they're trying to say on a theoretical basis is they're saying in independent events, probably Tuesday raining, it doesn't matter. It's independent of Monday. It will always occur. Okay, it will always, the chance of it does not get affected by whatever happened before. So what they're saying is then, instead of probability of Tuesday given Monday, they're saying probability of Tuesday given that Monday is going to rain is actually the same as just finding the probability of Tuesday. That's why that box here, this is key. Because what they're saying, the only difference in conditional versus independent event is just in that theoretical concept. Does it matter that the second day or the second event doesn't link to the first one or the one before that? And this is what independent event is saying. It's saying it doesn't matter. And if you think about your sort of real life scenarios, which events that doesn't have a linkage to things that happened before is something like flipping a coin. See, the first time you flip a coin, it's heads and tails. You would tell me the chance of getting heads is half, chance of getting tails is half. But then if you flip it for the second time, getting heads and tails, you never say that the chance of heads now changes because you got heads on the second go. You still say it's still half. The probability doesn't change. So the probability of getting tails on the second go, so tails on the second go, given that you had tails on the first go, actually doesn't matter. It's still the same as the probability of getting tails, which is still half. They're both the same. Get what I'm trying to say there? So that's where independent events comes in. Independent events is just stating that this probability, that branch, does not have an effect to, or does not link to the previous event. That's what it is. So once you change this, right, then the formula changes. So in this scenario, if it was independent events, then probability of M intersection T, chance of raining on Monday and chance of raining on Tuesday, it would still be 0.8 times by 0.6, but the difference is that T, okay, chances of Tuesday, this is now actually probability of Tuesday raining. Nothing to do with Monday raining. Okay, that's the theoretical part. If everything I just said doesn't make sense to you, it's okay. You can just memorize these two formulas here. It's just that students, when it comes to exams, especially year 12 students, they only memorize the rule. And so there's two rules for the same thing. So there's one where it's probability of A intersection B can either equal to probability of A times probability of B. So that's the first one on the top. Versus this one is saying probability of A intersection B is equal to probability of A multiplied to, probability of B times probability of A given B. Actually, I should swap that around. That's being replaced with probability of A given B times probability of B. That's the only difference. The difference between the two. So year 12 students get confused. They're like, do I use this formula or do I use this formula? And they don't know. And really, it's because of the questioning. So is the scenario you're working with, are they independent or are they conditional? That's the only difference. Is that second branch, so when I draw out the second branch, is this second branch, is that probability of Tuesday, nothing to do with Monday, or is it Tuesday linked with Monday? That's the difference. So if it's linked, it's conditional. If it's not linked, it's independent. That's all it is. Okay, so that's the key difference between the two on a theoretical basis. So probability of A, does it equal to probability of A given B? And that's what this first line is saying. Okay, that's all it's saying. Hopefully that last bit ties things for you, but that's the difference between the two. Okay, so exercise 8G is relying on the fact that the whole scenarios are going to be independent. And so in your case, what do you take out of this? What you take out of it is, if they are independent, this formula must be true. It always stays true. So probability of A times probability of B will give you the intersection. That's it. So in this whole exercise, you're just going to prove, are they independent or not? So here's an example. It says a selection of 14 hotel offers includes 8 with free Wi-Fi and 9 with a free breakfast. Okay. Whereas 3 offer both free Wi-Fi and then a free breakfast. Okay. Let's have a think of what they're trying to say there. Let A be the event choosing a hotel with free Wi-Fi, and let B be the event choosing a hotel with a free breakfast. This scenario has made it a bit harder to just jump in and draw a tree diagram. So it looks like I have to illustrate it in a two-way table or a Venn diagram. So I like using two-way table. You can jump in and do the Venn diagram if you like. I'm going to use a two-way table. So you either have A, which is Wi-Fi, or no Wi-Fi. Okay, so no Wi-Fi. Or B, which is your breakfast. Actually, B, breakfast is good. So B and B. What's it? How many hotels have free Wi-Fi? There includes 8 with free Wi-Fi. So 8 of them is free Wi-Fi. And then 9 with a free breakfast. So 9 is free breakfast, and there's 14 in total. So that means that there are 5 hotels without breakfast. And then there are 4 plus 2 is 6 hotels without Wi-Fi. Okay, and then they said 3 offer both. So 3, so that means that there are 6 here, 6, and that must be 0, and then 3 plus 5 must be like that. So if I were to draw a Venn diagram then, what we're saying is you got Wi-Fi, you've got breakfast. Now 3 of them offer both Wi-Fi and breakfast. Only breakfast is 6. So only breakfast is 6. So 6 plus 3 gives you 9 there. And then to get Wi-Fi, which is 8, well, that means this is 5 here. And then obviously there's 0 here because they already all add up to... So there's no hotels that don't offer free anything. Okay? Now here, what are we trying to work out? What's the... Did they even ask us a question? Oh, there we go. It's part B. All right, so I've done that bit. Now, they're saying find the probability of A. So what's the chances of getting Wi-Fi? Well, is 8 hotels, 8 out of the 14 hotels. So I would say here probability of A is 8 hotels out of the 14 will have Wi-Fi, which is the same thing as saying 4 out of 7. Okay, and then the second one is the chances of A given B. All right. A given B. So if there were A given B, using the rule, we know that conditional probability would say it's probability of A intersection B divided by probability of B. And remember, what this is saying is, what's the chance of getting a hotel with a Wi-Fi? Given that you already know that they've got breakfast. Okay, so in the scenario before, if you know that they got breakfast already, so if they got breakfast already, which this is the only hotels that they definitely got breakfast. And out of those 3 plus 6, which is 9, out of those 9 hotels, how many of those have Wi-Fi? What's the chance of getting a Wi-Fi out of those 9? So really, if I looked at that, the answer is clearly 3 out of the 9 there, okay, which is 1/3. But again, you could have used the formula if you wanted to find A intersection B, which is 3 out of 14, and then probability of B, which was 9 out of 14. And if you divide the 2, you will still get 3 out of 9. Okay, but my point is A given B is now 1/3. So state whether or not the events A and B are independent. Well, it looks to me, remember, if they are independent, what was one of the things that we knew? Probability of A given B has to equal to the probability of A. Because what I'm saying here is, what's the chance of getting a Wi-Fi given that you had breakfast? So breakfast is definitely on the table, right? So if you knew that was definitely occurring. Now, if they're independent, it doesn't matter if you had breakfast or not. The chances of getting A is still itself. So probability of A here, which we calculated, was 4/7, right? This is just chance of getting Wi-Fi. Whereas A given B was actually equal to 1/3. Clearly, they don't equal to each other. So therefore, it must not be independent events. Means both events are definitely conditional. It must not be independent events. Okay, so I'm using that one property. If they are independent, the chances of A given B must just be probability of A. It doesn't matter if I got B or not. And that's how you're proving it. Can you see how I'm proving the fact whether it's independent or not? And if I go back here, hopefully you understand the difference between them. It literally is just that fact. If it is conditional, then it means it relies on what had happened before. If it's independent, it doesn't. Probability of A will just be probability of A. So in this scenario, for it to be independent, probability of A and probability of A given B, if they were the same, if both of them were 4/7, that would be an example of independent events. Okay? Hopefully that gives you an idea, but all you're really doing is you're just proving one of those two rules here. So if you multiply probability of A times probability of B, and it equals to probability of A intersection B, okay, that would be proof that's independent. Or if you can prove that probability of A given B is equal to the probability of A, that's another proof that's independent. That's it. Okay? All right. Thank you, team. Hopefully that's enough for you to understand. I know at the start it might have felt a bit confusing. I know it's a simple rule, but I think the theory will separate the two so that you understand the difference between independent and conditional. Okay?